So now, horizontal asymptotes. So end behavior models are incredibly useful for us, but they don't actually find limits. They allow us to replace a function with an easier function while we find the limits. So if I find the limit if I want to find the limit as x goes to positive infinity of a function, I can replace the function with end behavior model to find that limit. But then if that limit is a real number, that horizontal line is going to be the horizontal asymptote. Same with negative infinity. And this can be tough. It's hard to know when am I doing limits as x goes to positive and negative infinity. It's hard to remember when should I use end behavior models. It's hard to remember how do I find horizontal asymptotes, because this is a pretty advanced limit concept. In Algebra 2, you probably were taught how to find the behavior of rational functions as they went to the left and right on a graph, but you probably weren't told that you were using end behavior models, and you definitely didn't talk about doing limits. If it helps, this triangle of concepts here, so horizontal asymptotes, end behavior models, limit as x goes to positive infinity of the function, and the limit as x goes to negative infinity of the function. These three things always go together. If I'm asked to find horizontal asymptotes, I'm finding these two limits. And to make finding these two limits easier, I'm using end behavior models. Or I could be asked, find one of these two limits. Well, if I'm going to find one of these two limits, I'm going to use an end behavior model. And if I get a real number for the answer to the limit, that's going to be my horizontal asymptote. The AP exam will not ask you only for an end behavior model. They'll ask either horizontal asymptote or one of these two limits. The end behavior model is used to help with the limits, which are used to find the horizontal asymptote. I have students call this triangle different things. Some of them call it Ha, Ebum, Lim. Others call it the Illuminati of calculus because it's like the all-seeing eye in the triangle. And it's one of those, we just have to practice this. This will make sense as we practice. It does not make much sense until we practice. It'll make a little bit, but not a ton. The other thing I want to kind of briefly mention is with a horizontal asymptote. So let's say here, y equals 5 is my horizontal asymptote. My function is allowed to cross a horizontal asymptote. Remember what I said in the vertical asymptote video. The word asymptote just means a line my function approaches. We couldn't cross a vertical asymptote because then we wouldn't have functions. But I can cross a horizontal asymptote and still have a function and still approach it. So it is common to see horizontal asymptotes get crossed, because what we care about is it approaches way out to the right or left where we can't even imagine graphing it. Things that are close to the origin, it's going to almost certainly cross your horizontal asymptote. So now calculating these. So if I deal with this first example, it's a really ugly function to write. But if I'm asked to find the horizontal asymptotes, what I'm asked for is, okay, I need to find the limit as x goes to negative infinity for this function. And I need the limit as x goes to positive infinity of this function. Because horizontal asymptotes require me to find those two limits. Because either there's going to be no horizontal asymptote both directions, they're going to have the same horizontal asymptote both directions, they're going to have different horizontal asymptotes both directions, or I'm going to have a horizontal asymptote in one direction but not the other. So I do have to do both limits. It's a lot of work and it's annoying. But fortunately, they don't ask a ton of horizontal asymptote questions on the AP exam. But it still requires checking both. Well, trying to do the limit as x goes to infinity of this function is a pain. So I'm going to figure out the right end behavior model to make that easier. So my right EBM, I see only polynomials on top, so I use the highest degree term. I see only polynomials on the bottom, so I use the highest degree term, and that simplifies to 3/2. So this means that when I do my limit, I can replace f of x with the right end behavior model. Please note, I haven't found the limit yet. I'm just replacing f of x with something easier to take the limit of. So I replaced, so 3/2 replaced the f of x. And now this is a much easier limit because the limit of a constant is the constant. And since 3/2 is a real number, that means that I do have a horizontal asymptote going to the right of y equals 3/2, because that's the equation of a horizontal line. So now I do this going to the left as x goes to -infinity. And again, I don't want to do the limit of this obnoxious function when x is going to -infinity, but because x is going to -infinity, I can use the left end behavior model. I see polynomial on top, so highest degree term wins. I see polynomial on the bottom, highest degree term wins, and that simplifies to 3/2. Again, that didn't find the limit for me, but the 3/2 can replace the f of x, and now I have an easier limit to calculate, or to evaluate, to be more accurate. Because the limit of a constant is the constant, and so my limit does equal a real number, I do have a horizontal asymptote going to the left of y equals 3/2. So I had the same horizontal asymptote going both directions. Now, in between the -infinity and the +infinity, whoops, my apologies. That is, the horizontal asymptote is being crossed by the function, but that doesn't matter because we're allowed to cross horizontal asymptotes. I just know that as I go way to the right or as I go way to the left, the function is approaching this horizontal line in both directions. Once we learn more calculus, we can sketch this function actually without using the calculator. Now, if I go to my k of x example from before, and I'm asked for the horizontal asymptotes, again, I'm saying, well, if I'm finding the horizontal asymptote, I need the limit as x goes to -infinity of this function. Oops, not f of x, it's k of x. And I need the limit as x goes to +infinity of this function. Well, that's an annoying function to try to do the limit as x goes to positive or -infinity on, but because x is going to positive or -infinity, I can use end behavior models. We already discussed that the right end behavior model was x squared, and the left end behavior model was e to the -x. And you can refer to the previous video on end behavior models if you need a reminder of how we reached that. Now, I haven't actually found the limit yet, but the end behavior model can replace k of x in each of these limits because x is going to +infinity or -infinity. So for the left, I have x going to -infinity, and I want to know what's happening to e to the -x. For the right, I'm doing the limit as x goes to +infinity of x squared. Again, I like the positive side first because it's easier for me. Well, as x gets bigger and bigger and bigger, x squared is getting bigger and bigger and bigger. So this is going off to infinity. Infinity is not a real number, so there is no horizontal asymptote going to the right. The limit as x goes to -infinity of e to the -x. This is a little bit tougher, but it's kind of how I came up with my end behavior model. If I plug in -10, because x is going to have to be a negative number if it's going towards -infinity. If I plug in -10, I get e to the 10th, which is about 3 to the 10th power. If I plug in -100, I have e to the +100. If I plug in -1000, I get e to the +1000. So e to the -x is getting bigger and bigger and bigger and bigger. It's not approaching any real number. So this is going to also be going to infinity. And since infinity is not a real number, there is no horizontal asymptote going to the right.